Welcome back to another episode of Computer Vision Decoded. We have taken over a year and a half hiatus on this podcast, and we're really excited to get back to it. I'm joined here with my co-host, Jared Heinly. Welcome, Jared.
Thanks, Jonathan.
All right. Well, as you know, since we haven't talked about computer vision in forever in this technology, Jared, would you say like a lot happens in a year?
Nothing's happened. I don't think anything's happened in the past
Not like
year and a half.
classical physics where you have a breakthrough every, every generation. I feel like with NVIDIA's GPU their hardware getting faster, people are able to pull off things that have never happened before. Yeah. I feel like I feel like every time I open up Codes with Paper, there's a new breakthrough. So
it's incredible. It's incredible how fast the technology industry is advancing right now.
It's definitely. Well, so for this episode, I just want to catch us up and talk about, like personal life, what we've been up to, and just do a little bit of roundtable between Jared and I about what we've been seeing in the industry that we're personally excited about, and just not go too in depth on anything. But I'd like to think for our listeners, if you're listening and there's a topic that you guys are like, wow, I wish they do a full episode on that, make sure that you guys, we'll be posting this, of course, on YouTube and socials. If you can jump on the comments and say, hey, I really liked that, let's do an episode on that, then that'll help us kind of guide what you guys are interested in, because, we're into it all. So, Jared, let's just start off personal. Like what's life been like lately for you?
Oh, it's been good. It's been good. For those watching in the video, my background's different than the previous episodes. So big change for my wife and I is we moved from Durham, North Carolina to Pittsburgh, Pennsylvania. It was a journey. It took us a little while to get up here, but we finally finalized our move back in fall of 2024. So
all right,
just a few months ago.
Steel City, is it also like tech city there? I've heard there's a lot of Meta has a office there. It's kind of a tech hub now.
It is. I've been impressed. Just when I first came here, I was like, okay, well, I know there's CMU, I know there's some other universities, but just being here now, going to a few different meetups and tech demo days or things, I'm deeply impressed with the tech community here. There are a lot of bright people working on a lot of interesting problems. Recently, I've gone to some robotics, like a robotics demo day and robotics happy hour meetup, and just talking to a lot of folks. It's incredible. And I love what people are doing, that intersection of the digital and physical worlds, because that's something I love doing. I love taking software and computer vision, having that measure something in the real world. And here are people building robots and systems that manipulate and perceive the real world. So yeah, nice. It's amazing space to be.
Yeah, I think it was 2018. I went to a robotics symposium at my alma mater at Oregon State University, and they had the head of innovation or something like that from HP there, and he did the closing keynote, I would almost want to say. And I love what he's kind of getting into that interaction of real world and robotics, and he was just saying, hey, I got a room full of students in robotics. Who told everyone was, you're not going to build something life-changing by just being a roboticist. He says, take your passion, because you all have some passion outside of robotics, and merge that with robotics, and then we're going to see some truly life-changing things. And he was just saying, don't devote your whole life just to building robots. It needs a purpose. And so that's neat to see you interacting with that, because we're always trying to build things to solve problems, not just do research for research purpose, which has its place. But yeah.
That's such great advice, and that I see that applies to everything, computer science. It's the same thing, computer science. It's just a tool. Software engineering is just a tool. Your greatest success and greatest passion, is going to be when you marry that with something else, And so, like you said, with these robots, talking to people who are using robots to create sandwiches in the food industry, or using robots for agriculture use cases, picking fruit off of vines or mapping out hazardous environments. It's really cool.
Yeah. So then talking about using this as a tool, what professionally, we at every point in Stock Bar Reports, we've been building away. I'd say we've been in founder mode, just heads down building over the last year and a half. What you've been up to in computer vision, or what? I know we we had talked I looked back, we had talked a little bit about real-time reconstruction on an iPhone, but we had just kind of started doing that. Where have we gone with that?
Yeah, we've taken that real-time reconstruction on iPhone and we've run with it. So that has been our big focus here over the past year and a half, 2 years, is taking as much of our computer vision algorithms and our sort of the intelligence that we've built up around stockpile measurement, so measuring the volume of piles of bulk material like rock, sand, gravel, mulch, things like that, and taking that and adapting those algorithms to run in real time on an iPhone. And so, yeah, around that, maybe 18 months ago, we had sort of finalized a version of the app, which the app called SR Measure, Stockpile Reports Measure, which could do on-device volume calculation of a freestanding stockpile. So if you imagine a pile of material sitting on the ground, you walk around that pile, you do a single loop, and as soon as you get back to the beginning, within a few seconds, you've got that answer there on the phone that gives you the 3D model, plus the volume, plus a nice visualization of the contours and the elevation and the risks around that pile. Since then, we've just continued to enhance it. So the other big thing we developed this over the past year was on-device bin or bunker measurement. So sometimes you have a pile that's not freestanding. It's not just sitting out in the middle of your yard, but it's stored inside of walls. So you might have some concrete blocks or some other structure where this bin with a pile surrounded by 1, 2, or 3 walls on its various sides. And so you can't physically walk around that pile and see it from all the angles. Well, then how do you measure that? How do you know how deep that bunker or bin is? How do you let the 3D reconstruction add in those constraints and know where the walls are? And so that's what we developed. It was sort of an intuitive on-device way to help people just download our app from the App Store, activate a subscription, and just follow the on-screen tutorials and leverage those robust algorithms to get that automatic measurement, to get that accurate volume calculation for their bunker or bin.
Yeah, so like to add some perspective on what Jared and the team has been able to accomplish, I joined this company back in 2013 in the summer, so it's been almost 12 years. And back then someone could take a video on an iPhone 4 and we could do a stockpile measurement on a freestanding pile, but that would require them to upload the data on the Wi-Fi speeds were not what they are now, especially for upload. Once they got up to us, we promised a 24-hour turnaround, and we stuck to that for most of the piles, unless something got really crazy. But I mean, we were still looking at like 12 plus hours per pile. And now, when you walk around a pile, I don't know how long it takes, Jared, but I want to say it's in the magnitude of seconds, not minutes. Yep. And that's crazy because that's all happening on the phone, not in a server. And then it was 2000, I'm trying to think, 2016, we added bunkers, maybe been a little earlier than that. And I remember even then, I was helping develop that. And the first bunkers that we managed to measure took me manually manipulating bunkers and creating primitives around it. I think it took like 2 to 4 hours per pile. And again, now there's not really any difference in time between a bunker and a freestanding pile right on the iPhone. So it's like magic, So just a reminder of whatever we talk about today. In 12 years, we'll probably feel like, wow, we didn't just take a single picture of a pile and know how much this thing. Oh man. Well, I guess on my end, I mean, I'm in the same seat I have been for 12. Well, I've been working in the same spot for 12 years, but I mean, it's not as much change on my end, but excited. I've been helping grow the stockpile reports and or measure messaging and getting people out there. I always find that it's magic, but the hard part is getting someone just to try it. And once they try it, they're like, whoa, I was not expecting it to be that fast or that easy. And then they start to think, oh, wow, well, if I got a measurement right away, what can I do with that? So the battle is just getting people to go out there and try it. And, in an industry where people typically, stick to the ways they've been doing things, that's the uphill battle. But once, it's sticky once you get someone to try it. Yeah. So switching gears then to computer vision and more of just like the science. Jared, we're just going to roundtable it. So I'm going to ask Jared a question. of like, I'm gonna have him bring up a topic and tell us what he's excited about it, and then I'll probably pile on, of course, and then he'll take his turn. And we just got a couple of these. We're gonna go through it, and again, this is a chance for you guys also to see what we're into and see if there's something there that you guys want us to explore in further episodes. So, Jared, what's like the top thing outside of building stockpile reports and SR measure that's more of the science that you've been into or exploring that we've been working on?
Yeah, absolutely. Maybe one of the big things I've been excited to follow and try to keep up with is just the recent advancements in 3D computer vision. My background, my PhD was in 3D computer vision, large scale structure from motion, photogrammetry, things like that. So I love anything related to 3D. And so to me, recent research, and well, I'm sure we're going to touch on it because I know, Jonathan, you have a lot of things interesting to say about Gaussian splats and NERFs and neural rendering and learning things like that. But for me, I love just seeing research papers that touch on just core 3D reconstruction, core geometry algorithms. And there's been a few over the past year. I know at CVPR 2024, ECCV as well, there were papers around global structure from motion. There's a GLOMAP paper out of ETH Zurich and I think Microsoft as well. But they're revisiting some algorithms where you say, hey, I've got a bunch of images. I need to figure out what's their pose, what's the position and orientation of each image, and how can we rethink some of the constraints and rethink some of the algorithms that have traditionally been used to solve that, and how can we tweak them a little bit to make it better or more robust. And so that's exciting to see. I also enjoy.
So just started to jump on GLOMAP, which is like it sits on top of COLMAP, right? So it's like we have this tool that's been around for a while, and they just swapped out a module of it almost, right?
Yeah.
And you didn't really talk about it. It's a lot faster, right?
Yes.
That's one reason to use it is that COLMAP, everyone complains it's slow.
Yep. And so that's one of the things. It's so like COLMAP, like you said, like that GLOMAP builds on top of COLMAP in the sense that you need to do some sort of pre-processing to your images. If you have 1,000 images as input, you need to go through, extract features from those images, find matches between those images to figure out, well, which features match with other features and other images. And once you have that database of matches, now you can choose to use either COLMAP and its incremental structure from motion algorithms, or you can use GLOMAP and its global structure from motion methods. And so I'm sure at some point in a future episode, I'd love to touch on this more, but just the pros and cons of incremental SFM, incremental structure from motion versus global SFM. And global SFM typically has been faster, but not as robust compared to incremental. But GLOMAP aims to say, well, yeah, we're going to still maintain that really high performance, that high speed, but make it more robust, make it on par in terms of accuracy and robustness compared to incremental SFM. So it's a nice advancement.
You see those charts that's like you can have fast, cheap, or easy, or whatever it is, or quality. Yeah. I can't remember what it was. It's like pick two, but you can't have all three. It's like I'm seeing some of these breakthroughs where it used to be these trade-offs. Now they're like, no, you can have it all.
Yeah.
I guess the trade-off sometimes is you need like a bigger GPU or something like that. But hardware is not as limiting factor as sometimes is the software can be, and just having faster methods now. So yeah. So all right.
I love
3D?
Seeing things like that. Anything in 3D, we're touching on those core structure from motion algorithms. Is really fun, and there's other works too. Again, I probably get off on a tangent, but just looking at papers that deal with multiple kinds of features, not just points, but adding in lines or other geometric primitives to help the 3D reconstruction process, or trying to use different types of cameras. So a lot of times, we as humans, we are used to the kinds of cameras that are in your phone. It takes a nice color image, you look at it, it makes sense. Well, there's another style of camera that I think is really interesting. I personally have not used any of the data, but I think it's really fun. It's called an event camera or a neuromorphic camera. And the idea is that for every pixel in the sensor, it's asynchronous update. And it just tells you, each pixel will tell you when the intensity of that pixel has changed by a certain amount. So instead of getting a full image of what it's seeing, you get these little events, these little pixels start firing whenever something moves. And so if your scene stays static, you get no data, but all of a sudden something starts moving across the scene. As those pixels change intensity, you get these really, really, really high, fast, really high speed, low latency updates. And so it's really nice for interactive, real-time, responsive computer vision. It has higher dynamic range, higher response rates, like no motion blur, things like that. But it's a whole new kind of data to work with. It's not typical pixels and color and images. And so there was some work this past year where people said, well, let's use these cameras, but do structure from motion from it. Let's figure out how the camera moved. Let's figure out what the geometry of the scene is, which is a really hard problem because you don't actually see the scene all at once. You only can perceive the scene based on these motion events. So again, really interesting stuff that I'm exciting to follow and see where
you may have just sent me down a rabbit hole. But also, I love the new cameras or some of these novel cameras that have come out, but they always have the one problem is the economy of scale, right?
Yeah,
so like everyone was like, well, why is it so expensive for, I asked this once to someone who comes from the background of military and stuff. And I asked like, why are these FLIR cameras so expensive? Like, and they're like, well, when you make millions of camera sensors for an iPhone or a smartphone or just even like a Sony camera, you can, each one gets cheaper to make because you've spent all the investment to get the factory to make it all. Yep. But when you're only making maybe tens of thousands, you don't get that. They have to charge a lot because it costs a lot just to even get the sensors made. And so I like these new cameras, but sometimes then it's like, well, they're hard to get.
Absolutely.
But that doesn't mean it's always going to be that way because, we're seeing like LiDAR. It's not a camera, but as a sensor, as industries adopt it, you just see the prices of those getting cheaper or even staying the same, but just the hardware gets better. So neuromorphic cameras, huh? Is that what they called? Or event cameras?
Yes.
Event cameras.
I refer to them as event cameras, but I've seen also in the literature, neuromorphic cameras.
Interesting. So, well, that might be an episode one day.
It could be. I would love to dive into that.
Someone wants to send Jared one of these cameras. I'm pretty sure he'd do something with it.
Oh, I would have fun. I would figure something out with it. Definitely.
All right. Well, I guess it's your turn to ask me.
I was going to say, enough about 3D classic structure from motion stuff. Jonathan, I know you've been doing some really cool things. Every time I log on to LinkedIn, you're always posting some new tutorial, some new video, some new demo. So what's got you excited this past year?
And I actually told this someone recently. They're like, oh, thanks for making these tutorials. They're actually, deep down, they're just my way of documenting how to use a research paper GitHub repository in the future. It's like, well, if I'm going to make this video, we didn't make the software. I'm going to make this a public tutorial because then it'll help myself when I'm trying to remember what I did. But also, I figured everyone else could benefit from that. And that's really wow. Like the first Nerf one was, I just recorded it so I could remember because it was kind of complicated. And then people liked them so much. So I just make them.
That's nice. That's smart.
I'm gonna stay in the same category than you're talking about. So about like structure from motion and that just getting point clouds and that raw data. I've been really into seeing what they're doing with neural networks in that pipeline. So there's Duster and then there's Master, which is just like a better version, and then now there's even newer there's one called Cutter, I think it is. They're just taking the same research and just keep pushing it along and playing on the same fun name of it. But I'm always just, the first time I used Duster, I took two images that were near 90 degrees different in orientation. So imagine like a picture of your desk and then a picture of your desk from like the complete opposite side. If you do that with stereo pairs or you're trying to do classical 3D reconstruction, it's not going to work. Things look too different. However, with this, it's just like, oh yeah, no problem. You get a point cloud and you get two camera poses, and you can even throw like two types of cameras. So I could use like my iPhone, and I could use like a drone or whatever I want. It does not care. It just figures it out. and it's got this. The one downside, it's got this really big model checkpoint because it's using some neural network, so it's got this big file sitting in the middle, but it's also fast. Like it's like instant at this point. So I've been into that. The one limiting factor, I always like to talk about like the pros and cons of it. So it's cool that you can just throw stuff at it and you just get sane results. They're not necessarily nearly as good or as detailed as if I stick to using, like Colmap or one of these software that's really tailored for this. But if I'm just trying to get camera poses, it's fast. It's pretty close to accurate. And but the downside is you can only throw like a few thousand images on the latest version before you start to like need to like almost use a server of GPUs because it's all now it's using GPUs. And so we can't like just throw this model on an iPhone and run around. It won't work. So, but it could be useful in the future. I'm just thinking the way our industrial cloud vision at every point, I'm going to get a picture of every point on the planet or every picture at a rail yard. I mean, there's no reason why those aren't all just fed through some sort of pipeline to a server cluster that's able then to take all these sources and start to build a 3D model really quickly. And it doesn't matter if those pictures are all perfectly lined up and with the right amount of overlap. It should be able to get us like a rough model of the space all the time. And then, compute power can always happen in the cloud if it makes sense. So yeah, I'm just really into that. And I'm seeing more, like I just put a YouTube video out how to do instant splat. So it's like 3D Gaussian splatting in 60 seconds. I think of course, the tutorial I showed took like 90 seconds. And people are like, well, that took longer than a minute. But when you're recording your video and you're doing other things, your computer was a little bogged down. And I ran it with like the GUI. If you run it with just headless, it goes faster. I did do one in like 50 seconds or something like that. But just the fact that I could, it's using that, again, that Duster model, or I think use master in the background, and that just speeds it all up. It's just like you can take two pictures, they're semi-coherent to each other, and then it creates the whole entire model output. Was just mind-blowing. So
it's amazing to me. Like the first time I saw machine learning based pose estimation, I was like, how is this possible? Because for me, I was so used to pose estimation being done via, explicit geometry. Like, it is triangulation. It is a rotation and translation between two images. I'm trying to estimate, an essential matrix and then decompose that and then triangulate my points. And, it's all geometry. It's math that I can understand. But, all these machine learning models that it's like, it's magic. You give it the two images, like you said, that example where you can have, that such a wide viewpoint change, the front of a face and the side of the head, so these two angles that traditional machine learning has, it's impossible, such a wide baseline matching, where now these machine learning models are able to do that reasoning.
Yeah, I mean, it does feel like magic just because I don't have the background. You have Jared of learning the math and the science behind all this, but it's almost like some of it's being like rewritten, saying, oh, okay, this is traditionally how it's done, but now we add this one neural network in. You can just scratch out that principle and say, okay, it goes. Of course, it's not as accurate, but sometimes accuracy is not 100% the goal. I mean, there's some accuracy. It's still accurate. It's just not as accurate. There might not be the goal. So,
and there's trade-offs, like where, maybe it isn't as accurate because maybe your camera is well behaved and you have a great understanding of the focal length and the lens distortion, and you understand the geometric model of that camera, and so a geometric based pose estimation works really well. But there are cases where, well, maybe I don't really know what the lens distortion is, and it's something that I can't model easily. It's something that's really complex, or I've got just some weird imaging platform or weird, camera motion or rolling shutter has been introduced to my image that, for whatever reason, my algorithm's having a hard time understanding. Well, a machine learning model can compensate for that. It can potentially learn more complex, higher dimensional functions on top of that pose estimation that the typical old school algorithms may not have captured.
Yeah.
And so there is trade-off. There's times when, yeah, that geometric model is going to be better because things are well behaved and we have a great geometric understanding of the problem we're dealing with. But there's other times when machine learning, yeah, like that matching 90 degrees, different of viewpoint, it wins.
And maybe that's all you have to go off of. We've had people reach out to us. Hey, you guys do 3D reconstruction. I have a bunch of images that were taken in the past, so we can't go take new ones of some specific scene. And can you guys reconstruct it? We take a stab at it sometimes, but you start to look at the pictures and say it's not going to work. But now it's like, well, maybe it will work with this. With this. So you give it a shot. So I am going to throw out one more caveat here. This is all. You can go play with this stuff, but you can't build a product yet unless you license it too. That team smartly around the Duster has decided to make it licensable, which is great. But like, don't just because something's on GitHub doesn't mean you can just go use it and sell things on it. But they open it up so you can go play with it and build it in your own products, and then decide, hey, I want to use this. Let's license it. So, I think I see a lot of people start to get excited. And I was like, well, this one's not open source, so play with it. They don't care about that. Just don't go building a product and think that you can just skip that fact that they require you to license it. So, all right. So, okay, what else are you interested in? So, let's just move out of the world of classical 3D reconstruction. Anything else caught your eye lately?
Well, I was going to say just what you mentioned, talking about pose estimation, from images using sort of machine learning based stuff. I am loving all of the work now around SLAM, so simultaneous localization and mapping, because again, there's traditional SLAM algorithms that rely on feature matching, feature tracking, pose estimation, bundle adjustment, things like that. A lot of times using just 3D point-based representations for that map. So as that camera, so you imagine a camera moving through a scene, so you're holding up your phone and walking through an environment, or you've got a robot that's got a single camera on the front. It wants to figure out where it is in that environment as well as map the environment that it's in. And it's doing that mapping process as it's moving along. And so traditional techniques, have used these just 3D point-based maps. Whereas now, with the power of NeRFs and Gaussian splats and machine learning, you're starting to see these richer representations for that map and that mapping process. So there's been countless works now around using a Gaussian splat or a NeRF as the representation for SLAM. So instead of using just explicit 2D to 3D point correspondences, now you're building up a Gaussian splat, a photorealistic representation of the environment, and using that for your localization tasks.
Which is, I see it like is it visual odometry they call it?
Yep.
And you see some projects like that saying it's like, well, it's building a visual representation as you're moving around versus just a point cloud. And then it's almost re-referencing itself off of the output. Did it match what it just saw? Trying to understand the papers. I saw one came out like a week ago, and actually had the code out, which I was really interested in. It was basically taking a Gaussian splat scene and then being able to better refine your camera pose position and your intrinsics all off of that. So it's kind of like it creates one. It's like this reinforcement loop or something's happening there. I don't quite understand sometimes what's happening, but all I know is at the end, it creates a Gaussian splat, then it gets better camera, and then you get a better Gaussian splat. And it's almost like, and that might not be SLAM. I can't remember if that one's SLAM, but I'm seeing that sort of thought is instead of just, going off of a few key points, it's going off of the whole visuals.
Because it's almost like what you're describing sounds almost like bundle adjustment, but instead of using 2D, 3D point correspondence, like these really sparse constraints, what I'm seeing is by using splats or NeRFs, you're getting a richer, more complete representation of the visual appearance of the scene, which then gives you more constraints and more insights to say, hey, do I have an accurate representation of that scene?
And this one was like forward facing. Like you don't have to do like a bundle adjustment. You got to usually do like some sort of like loop. Something. This is more of like, hey, I got a few forward facing images. Like they bundle adjustment without a loop closure is what I'm thinking.
So like relative like a local refinement, saying, okay, I've got a few camera poses all kind of looking the same way. How can I optimize their arrangement?
So with all these SLAM projects, like how how would you see using SLAM? I mean, I see the people who put on like the big SLAM backpacks or the handheld SLAM scanners, which are cool, and they usually use a lidar puck, right, to do something, to localize themselves. You're talking more like vision only SLAM, right?
That's yeah, and I should say like there are SLAM is a broad category. Like you
Mm-hmm.
mentioned, like you can use other sensors, so if you have a LiDAR scanner, you can do, LiDAR based SLAM or visual plus LiDAR. A lot of times LiDAR, if it's on a robot, you may have odometry from the wheels, wheel encoders. So
Mm-hmm.
where the robot
Oh,
can say, oh,
interesting.
I spun the wheels, 10 times. And so I moved forward 1.2 meters or whatever it is. So you can combine that in as constraints. Um, or a common kind of SLAM that I've worked around would be visual inertial SLAM. So we have camera plus some sort of inertial sensors, like your accelerometer, your gyroscope, your magnetometer.
Is that what the
Um,
iPhone is?
exactly, that's where I
Yeah.
was going with it. So the most common application of SLAM that people may be familiar with or have worked on would be AR kits, so augmented reality. Anytime you use augmented reality on your iPhone or on Android, or if you've tried out HoloLens or
Mm-hmm.
Vision Pro from Apple, all of that is running SLAM. When you're using augmented reality, it initially knows nothing about your environment, and all of a sudden that device needs to figure out really quickly, well, where am I? What's around me? And then as you start moving, figuring out how you're moving in an environment so that those virtual objects in the scene can be properly placed and tracked in that environment.
So when you ever use, I have not used an Android AR Core version of SLAM, but I'm assuming it's kind of like AR Kit. But
Yep, same
in
thing
these
basically.
phones, when you sometimes launch an app that likes to track the world using SLAM, I notice it always says like move your phone around. Is that
Yep,
what it's doing? Is just trying to start to like anchor itself to where you are and
absolutely.
initialize that. Hey, okay, now I have some understanding of the scene, and
Yep,
now I
yep.
can keep moving.
Yep. It's going through like a bootstrapping initialization phase where, and then in those first few seconds, it's trying to, as you're moving that phone, it's trying to start to triangulate points in the scene,
Mm-hmm.
so that it can figure out, let's start to build up that map. If it's got an accelerometer, it's also going to be taking acceleration readings so that it can fuse that with the visual data to try to estimate the scale of the scene, saying, oh, is that wall in front of me, 1 foot away, or is it 10 feet away, or 100 feet away? And so
Mm-hmm.
it does some initialization to try to figure out, well, hey, where am I? And okay, good enough. Let's start running. And then it can do the refinement, like you mentioned before, where it's, maybe I haven't done a complete mapping, but as SLAM runs, there is local refinement that occurs.
Yeah, I think
So
there's a
that
lot
happens.
going on in these smartphone based SLAM that we're not even aware of, and I've become more aware of as I've played with it. Thinking of Room Plan, where you can
Oh, yeah.
literally stand in a room, wave it around, then it'll start saying, "Move it to the corner of the room and to the top of the ceiling," and then move it across, and it tells you in very easy to digest words where to move, and it just starts building the room. And I know, like, I think that might use the lidar as well to help get depth, but
Hmm.
the fact that it like can sense a corner, and I'm sure it's using those sort of features as well to anchor itself, and then it knows it's a couch, it's a kitchen sink, it's a refrigerator, and
Yep.
that's again, it's like there's a whole layer of machine learning of object recognition and segmentation that's going on. That, like, the great thing is a person doesn't have to know about that. It's just
Hmm.
again, feels like magic.
Yeah.
Feels like you're this incredible person scanning the scene. When really Apple's doing all the hard work for you, but they've kind of built that whole stack. They have the whole sensor stack, they have the whole software stack, and the machine learning behind it, and it's really neat what you can do. And it's just, I feel like it gets better every time.
Yeah.
Like sometimes I'll scan it. Everything at one point was all like rectangles, and now you scan it, and it's like, oh, I got the arch from my
Hmm.
from my doorway now in there. It's gotten smarter.
Yeah.
So
Yeah.
yeah, it's
Yeah.
so
It's
where do
it.
you see this being used then? Beyond like the smartphone AR kit world.
Sure. I mean, yeah. So the smartphone, world that helps consumers, but I think a lot of these techniques, maybe it's going biased because I've been talking to roboticists recently, but I see a lot of applications for this in robotics. Whether that's humanoid robotics, trying robots trying to navigate and understand interior environments, or whether that's robots in, industrial settings or
Hmm.
outdoor, see that, autonomous delivery or autonomous driving. There, there's situations when, a robot needs to understand its environment, and it may not have been in this environment before. It's a new space. It needs to make sense of its world. And so having advanced SLAM algorithms that can help that robot navigate are very important. So I continue to see this, helping, autonomous navigation.
Yeah. Yeah, well,
Definitely.
okay, so now you're dovetailing into what I was going to say is my next thing. So,
Go for it.
I don't think you meant. I don't know if you meant to do that, but maybe you did. I mean, I've been excited. I watched the what do you call it? NVIDIA did their keynote. Jensen did the keynote at CES and announced to the world Cosmos, which is their world foundation model. And of course, me being me and curious, thought, oh, that was a GitHub repo. I'm going to play with that because I am fortunate enough to have a GPU from NVIDIA that can run it. It doesn't, you need more than just like a base gaming GPU. You don't need like their super expensive ones, but it's a world foundation model. So again, they've also, in Jensen's new thing is physical AI. So like understanding the physical world. And
Mhm.
I think is interesting is most of the people I like on LinkedIn or X and all these places are all excited about the media and entertainment space and like, oh wow, God and Splatting, I can use that in film. But Nvidia's thought and how I think we as every point think is more of like, well, we're here to solve real world problems. I know film is a real world problem. If you're a director, that's a problem for you. But
Yeah.
we're more like, how can we help industrial supply chains be more efficient? And to do
Hmm.
that, we know the future is probably going to be somewhat autonomous. Well, it's going to be autonomous and it's going to have robots. It's going to have, we're already seeing it with drones. You're already seeing it with all kinds of advancements. So you need to understand that 3D world. And that what NVIDIA did is they took 20 million hours of imagery and they trained a neural network to like understand scenes and the 3D context to it. So it should understand like wind and how that interacts with objects and 3D space and like things like that. And so I think people are a little confused by what it is at this point. I think they think that, wow, I can just say, give me a 3D scene of a robot driving through a warehouse and it'll create like a full omniverse 3D scene. It just, at this point, Cosmos has a few backbone things they released, but at the end, it's just making what's called diffusion or autoregressive models for making images and video feed. So, like, you want to reinforce SLAM, I think is interesting. If you wanted to understand the physical world in which a robot's going through, it's crazy the amount of data it needs to really understand, specifically edge cases. Like it can pretty quickly understand, okay, I'm in a warehouse, these are crates. But all of a sudden, a cat's on a crate. It's like, I don't know what the heck that is.
Yeah.
Not that you probably see cats, but there is so many edge cases in the world. It's ridiculous. And so what they're trying to do is say, like, okay, I can take, they have what's called fine tuning. So now I got this world model, which is this base model that should understand the world. And then I can say, okay, now I'm going to give it 10,000 5-second clips of a specific warehouse environment in which I want to now deploy my robots in. And then it'll say, okay, now I know more about where exactly you want me to do. And now I can say, take this picture of a robot in the warehouse and give it a bunch of theoretical situations. And it can then just spit out, tons of variations of that, and which then you can then go reinforce the robot on all these edge cases. Like for one, I think of driving cars too. It's like you're not going to take a child and throw it in front of the car and say, "Let's train it to stop before they hits the kid." But
Yeah. Yeah.
we can do that, Or what happens if a crate falls over while it's driving? And it'll learn these things. And I like that they're taking the same kind of thought of us. It's like we're going to build generative AI, but to solve real world tasks and not just make interesting movie trailer snippets, which again is really cool. Like I like a
Hmm.
lot of this generative AI video stuff, but like it's to me it's got a limited use case versus like let's make the world work more efficient. And of course it all requires lots of compute power.
Sure.
It takes 25 minutes on my pretty new GPU to get 5 seconds of video out. But on one of their, NVIDIA's advanced H100s, that's like 5 minutes or even shorter. Now they have the new Blackwell coming out. Everything's getting quicker and quicker. But just that thought of, I'm thinking like every point. What if, what if we're trying to understand trucks or something moving through a quarry? Well, you can only put so many cameras up and just record images, and from so many viewpoints. Where I can start to say like, hey, I want novel viewpoints, or what happens if it's a drone flying over, and start and get all these, situations, and then build our own model on top of that. And that's what it is to make your own model bespoke to what you're trying to do.
Yeah.
Yeah, it's fascinating what they're able to achieve with that.
Yeah. That whole goal of digitizing reality so that then you can use that. You're saying, okay, yeah, well, sure, yeah, use that for entertainment, but using this to help train more robust, more reliable algorithms by having that robust, flexible representation of what is possible and generating
You're using
things.
Computer vision to make better computer vision.
Yeah.
Getting back to that reinforcement loop. I'm seeing a lot of that. Now we're in the world of training things off of and making neural networks. We're able to, all we need now is more data. And so we're making up ways to make more data without having to go out in the real world and get that data. So
and that's so important, because like there are some spaces where there is already a wealth of data. Like if you're looking at perhaps certain consumer applications where people are taking photos and sharing it. You may already have a ton of, fashion photography or food photography, or, so there's certain applications where you already have a lot of digital data, readily available at your fingertips. But I think what I heard you kind of touch on was, well, there's certain, industries, practical problems, which maybe where you don't have that wealth of digital data available. So it's like, well, how do you digitize reality for an under-digitized environment? And so that's kind of the space that, we're playing in with Every Point and Stockpile Reports, is these quarry yards, these outdoor, stockpile sites where, you don't have cameras, you don't have laser scanners. They're constantly digitizing these piles. So how are you going to train models when you don't even have digital data for that?
Right. And it's expensive to go out in the real world and collect it. And so you do as much as you can. But at what point do you collect enough of it that we can start generating its own, our own, and there's probably some known things about quarries by now that it's like, that's the great thing about self-driving cars. It's like, there's some rules that it should know by now. And I think of Tesla, their newest self-driving model, or whatever they want to call it, autopilot, where they did it all off visual, but there's some things it knows, like you stay in a lane. Usually, I mean, there's, again, the edge cases, but if it's trying to replicate a real driver and it sees that 99.9% of the driving is in the right-hand lane in the United States, it's going to know, okay, that's what we do here, and stick to it. And so with quarries, it's kind of like, well, maybe it doesn't know to stick in a right-hand lane when trucks drive around. There's no lanes, so it's got to like learn its own methodologies around that. So that's where I like to look at these projects, like Gaussian splatting and all this stuff. It's like, well, we might not be using it today, but it might be kind of new. And tomorrow we might decide, wow, okay, we realize where this really helps. And instead of being, okay, we see someone who used it in an application that might work for us, I like to think that we've already then explored it a little bit. And so we can come in and pick it up and start playing with it and trying it out without also being behind. And I'm sure as a PhD, like you've done so much research in one silo to get that PhD, but you still want to be able to keep your blinders off to be able to say, okay, what's new, tangential to what I have lots of expertise in, so I can figure out how that implements, or maybe hire the right person one day to help that.
Definitely.
So I know we're getting close to the end of this episode. We didn't even talk about Gaussian splats. I know that was on both of our lists. What, just really quickly, what are you excited about in that? Like, I know, I mean, that's what I do as a hobby almost. So
I love one, that they exist, because it's, when nerfs kind of came out, and they were, that was neural rendering, straight up where, you've trained a machine learning model to generate that image, and it was a black box. Whereas whereas Gaussian splats have a much more understandable representation. It's Gaussians in 3D space that then you use to render your image. It has a much better match to current hardware and rendering pipelines, so they're fast, faster to train, faster to render. And I love that they're built upon 3D reconstruction. In order to train a Gaussian splat, you need to start with some sort of camera poses or some sort of point-based initialization of the scene. As a lot of people use off-the-shelf structure from motion to bootstrap it and get it running. So, yeah, again, it touches on my key loves of 3D and visual things. So,
You know, and it's been fun to watch. Like, I like to look at the fringe papers coming out, like solving small problems.
oh yeah,
That so like de-blur Gaussians, which is basically what do you do when you have blurry data? How can I de-blur it, or how can I deal with rolling shutter artifacts to still then get a good output? Or even I've seen they just deal with the most minute problems. But what's happening then is like through Nerf Studio, the open source people, those guys are saying, or those researchers are saying, oh, I think I can merge this code into existing, models and open source it, and then just keep making that one, that's called G-Splat. It's like the open source one. And then, the outputs I came out with a year and a half ago compared to today don't even look the same. And they're dealing with all these, fringe issues. And it's, people say, oh, this looks great, but this looks great, but, and they're like, well, okay, now someone has done a paper on that.
Yep.
I love 40 as well, but the problem is, again, I don't have a way to get data for it. So, even if I could someone could load me all the cameras, you still got to build a rig and understand how to place them all. There's a lot to it. So,
temporal, just 3D reconstruction, challenging and interesting enough. But as soon as you add that temporal component to it, that's a whole nother ballgame.
Yeah. Well, I feel like we should do an episode on 3D Gaussian splatting in the near future. I think it would be fun to dive into if we could get like another expert on as well. I know when we did Nerfs, we had Matthew Tansik on, and he did a really good job at explaining what Nerfs were, and because no one knew. But now if we could get someone, even him, I'm sure, because then he knows that world as well, or someone to come on and explain how 3D Gaussian splatting works to a semi-technical person, but obviously someone who doesn't have credentials like PhD on the end of their title would be great. I know I have a good idea how it works, but no one can elaborate better than the people who research it. There's this whole thing about projecting splats and then rendering it onto a 2D frustum and then iterating, and there's a whole duplication and pruning. And I understand how it all works in theory, which is great. Enough for me to go out and master it, but I would love someone to really break that down and really make it tangible, so I could just say, hey, if you're on your journey and you don't understand why you're getting these results, this person explains in very easy to digest terms how the sausage is made. So now you can get the best output possible. And I think that's it. Like, also image capture is one I've been really diving into, because it is, you have to stick to photogrammetry principles for the most part, because you still have to get camera poses and a point cloud, but it isn't a 1-for-1. So, it's like you want to do everything, but further out, because you can get context and, things that you might do in photogrammetry will work, but might not be the best. So, yeah that's what I've been liking to get into.
Yeah, that'd be. Well, I was going to say, and just touching on Gaussian splats, I'm excited to also just explore that, boundary between, classic structure from motion, and new machine learning based 3D reconstruction. And diving into sort of the pros and cons there and the strengths and weaknesses. I know we tried to touch on a little bit here on this episode, hinting at some of the things that are going on, but I know that the research has definitely advanced and continues to advance in that space. So that'll be fun to explore in the future as well.
Yeah, definitely. I think there's a lot of research going on there. The joke is you go to the CVPR and that's what everyone's talking. That's half of what everyone's talking about. And there's a lot of other stuff going on, but that for some reason it's visual. So I think people get excited. Some of this other stuff is very important, but not as easy to showcase in a visual, and that having a visual medium always makes it more exciting. So
yeah, definitely.
So, all right. Well, that concludes our first. We're back. I think our goal is to post one of these once. I'm going to try to go for weekly if Jared can hang on with me, because there's so much for us to catch up on. And again, I appreciate everyone who tuned in today. We'll have it, of course, on all your major podcast players, and also on YouTube under the Every Point channel. And if you comment on that and you see something you like in this episode that you want us to go deep on, let us know. We'll either be doing it solo between the two of us, or we can see if we can get a researcher on. Hint, maybe Jared can reach out to some people about glow map that he they all come from the same world, so it's pretty easy for us to reach out to a PhD, and they they're amongst their peers and then me. So, but it was great having you on, Jared. And we'll see everyone in the next episode.
Cool. Thanks, Jonathan. See
you.
you
All right. Thanks, Jared.